Here we start exploring some important ideas about numbers, measurement, and scientific data. We're going to look at how numbers that seem exact can actually be a little more complicated than they first appear, especially when it comes to measuring and understanding uncertainty. This will help us think more carefully about the way we handle data and interpret results in scientific work and beyond. Let's get started. In science, measurements are never perfectly exact. We define physical quantities by the methods we use to measure them, but every measurement has its limits and uncertainties. Our job is not to reach impossible precision, but to carefully assess and communicate how much uncertainty or error exists in our data. This approach helps us understand how closely our measurements represent reality and allows us to make meaningful conclusions despite the inherent imperfections. Random errors happen because of small, unpredictable changes in things like the environment, the person taking the measurement, or the instrument itself. These cause the data points to scatter around in no set pattern, which means the results are less precise and more uncertain. The good news is that we can minimize these errors by taking multiple measurements and calculating the average, which helps even out the random fluctuations. On the other hand, systematic errors come from consistent problems with the equipment or method. These errors skew all data in the same direction, causing the results to be inaccurate. Unlike random errors, simply repeating measurements won't fix this. Instead, we need to find the source of the problem and correct it, either by fixing the device or adjusting the data by subtracting the known error. Understanding these differences helps us improve the reliability and accuracy of our experiments. What this illustrates is a systematic fixed error in measurements, where the scale consistently shows a weight that is higher than the actual weight. For example, an object that weighs 6 kilograms is displayed as 8 kilograms on the scale. Similarly, when nothing is placed on the scale, it still shows 2 kilograms, and when a 3-kilogram object is on the scale, it reads 5 kilograms. This kind of error remains constant regardless of the actual weight being measured, indicating the scale has a calibration issue that adds a fixed amount to every measurement. Understanding this helps us recognize and correct these errors in practical situations. When we talk about the average, it usually means the value is close to the bullseye or the target point we want to hit. In other words, the average measurement tends to be near the accepted reference value, showing good accuracy. However, it might not always mean all the data points are tightly grouped together, so precision could vary. This helps us understand that an average being close to the target is a sign of accuracy, even if the individual measurements vary more widely. If we consider A as a measurement, then it's important to think about the uncertainty connected to that measurement. Absolute uncertainty tells us the range within which we believe the true value lies, and it's expressed in the same units as the measurement itself. For instance, if we measure a length as 20 degrees Celsius plus or minus 2 degrees, the absolute uncertainty is simply 2 degrees. But to understand how significant that uncertainty is, we also look at percentage uncertainty, which shows the uncertainty as a portion of the total measurement. This helps us see the relative quality or scale of the possible error. For example, a 1 millimeter error on a 10 millimeter measurement is a 10% uncertainty, which is quite large. However, the same 1 millimeter error on a 1,000 kilometer measurement is almost negligible, only about 0.000001%, showing how percentage uncertainty gives better context to the size of the error compared to the measurement itself. Let's move forward and apply what we've discussed by working through an example involving a bag of apples. Imagine we buy a bag at the grocery store and weigh it. The average weight comes out to 5.1 pounds, but there's an uncertainty of plus or minus 0.2 pounds, which comes from the limitations of the scale. To understand how reliable this measurement is, we calculate the percentage uncertainty by dividing the absolute uncertainty by the average weight, then multiplying by 100. In this case, that's 0.2 divided by 5.1, giving about 3.92%, which we round to 4%. This tells us that the weight is 5.1 pounds with a 4% uncertainty. Because this percentage doesn't have units, it gives us a clear and straightforward sense of how reliable the measurement is, showing that it's quite accurate. When we measure things, we rarely just rely on a single number. For example, calculating an area requires both length and width measurements, each with its own uncertainty. These uncertainties don't just disappear when we use these measurements in calculations. They combine and affect the final result. To handle this properly, we use mathematical rules that help us track how these errors propagate, especially when we add, multiply, or raise numbers to powers. This way, we can better understand the accuracy of the results we get from combined measurements. To find the uncertainty when adding or subtracting measurements, we just add their absolute uncertainties together. For example, if you subtract the internal diameter of a pipe from its external diameter to find the wall thickness, you take the uncertainties from both measurements and add them. Here, the external diameter is 102.8 millimeters, with an uncertainty of plus or minus 0.3 millimeters, and the internal diameter is 101.4 millimeters, with an uncertainty of plus or minus 0.1 millimeters. The difference, which is the wall thickness, is 1.4 millimeters. Adding the uncertainties, 0.3 plus 0.1, gives a total uncertainty of plus or minus 0.4 millimeters for the wall thickness. This simple rule helps us understand and account for the possible variation in our measurements whenever we combine values through addition or subtraction. Now let's move on to the next rule, which deals with multiplying and dividing measurements. When you multiply or divide values that each have some uncertainty, you combine their percentage uncertainties by adding them together. This means if you have two measurements, A and B, with their own percentage uncertainties, the total uncertainty in the result, y equals A times B, or y equals A divided by B, is just the sum of those individual percentages. This approach works best when the uncertainties are relatively small, like a few percent or less, ensuring the final error remains accurate and mathematically valid. Now, let's look at how uncertainties behave when we raise a measurement to a power. The key idea here is that when you raise a value to a power, you multiply the percentage uncertainty by that power. For example, if we have y equal to a raised to the n, then the percentage uncertainty in y is n times the percentage uncertainty in a. This makes sense because raising a number to a power is like multiplying that number by itself repeatedly. So if you square a value, you're effectively doubling the percentage uncertainty. To put this into a concrete example, if a equals r squared, it's the same as saying a equals r times r. The percentage uncertainty in a is then the sum of the percentage uncertainties of both r values. Since they're the same, it's simply 2 times the percentage uncertainty of r. This rule helps simplify how we handle uncertainties in calculations involving powers. Building on the previous points, imagine how a tiny uncertainty in measuring the side of a square tile affects its overall area. The length is given as 84 millimeters, but it could actually be off by half a millimeter in any direction. Since the area is the side length squared, this uncertainty doesn't just add up, it multiplies, spreading across both dimensions of the tile. This means the small measurement error becomes much bigger when you consider the entire surface, which is important to understand when precise area calculations are needed. We start by finding the percentage uncertainty of the side length, which is the uncertainty divided by the measurement itself. So 0.5 divided by 84, then multiplied by 100%, giving about 0.6%. Next, we apply the power rule, since the area depends on the side length squared. This means we multiply the side's percentage uncertainty by 2, resulting in 1.2% for the area's percentage uncertainty. Finally, we convert this back to an absolute uncertainty by multiplying the total area, 7,100 square millimeters, by 1.2%, which equals 85 square millimeters. So, the area of the tile is 7,100 square millimeters, plus or minus 85 square millimeters. As we move forward, it's important to remember that scientific inquiry relies on careful scrutiny and evidence. Every measurement we make has limits, which means we can never claim absolute certainty about any conclusion. Instead, we acknowledge the inherent uncertainty in what we know. By precisely calculating errors and understanding how they affect our results, we create clear boundaries that honestly reflect the extent of our knowledge. This approach helps us stay grounded and ensures that our understanding remains reliable and transparent. As we wrap up, it's important to remember that uncertainty doesn't undermine science. It actually supports it. Science gains its strength and reliability by openly acknowledging uncertainty, which ensures that predictions and measurements are honest and trustworthy. Without recognizing uncertainty, measurements would just be guesses. Instead, when uncertainty is clearly defined, it becomes the foundation that gives scientific truth its solid ground. This perspective helps us appreciate that the very nature of science is built on understanding its limits as much as its findings.